Okay, so my question was about to draw an engineering stress graph for ductile metal, ductile polymers, ceramics, glass, and natural rubber, and to basically describe about it. So first we have metals. Metals for their strain versus stress, which is strain in the x-axis and stress in the y-axis. Uh, the curve shape gradually increases will like with a well-defined yield point followed by a strain hardening, as you can see in the graph where it only stops at a certain stress point. Second, the yield point, which is basically the peak, clear like it has a clear yield point where plastic deformation begins, and at the peak, that's like where it doesn't come back. And also, reasoning for this is because like metals like steel and aluminum, which is shown on the left, undergo plastic deformation through the movement of dislocations. The yield point marks like where it deforms, and that's like when the dislocation like occurs too much where it cannot come back. Next, we have thermoplastic material, also known as ductile polymers. The curve shape is generally exhibits a gradual smooth increase in stress with strain, but the yield point may not have a distinct yield point. Instead, it elongates significantly before failure. So as you can see, there's a very long line before it finally breaks at that point. The reasoning for this is because polymers like polyethylene and um, nylon, they undergo plastic deformation and exhibit like necking before an ultimate failure due to their molecular structure and chain entanglements. Next, we have elastomers, also known as natural rubbers. The curve shape shows a relatively gentle, elongated curve, and the yield point displays a yield, uh, and the yield point displays a yield point followed by a straining hardening, as you can see there. Um, the reasoning for this is rubber is a polymer with a unique ability to undergo large elastic deformations. The initial yield point is followed by strain hardening due to molecular reorganization. So as you can see, there's like this curve until it reaches this point where it starts to harden, which is like straight down basically and go up. Next we have ceramics like oh ceramics, glass and stuff. They are similar because they're both ductile, which meaning they can break easily. Oh no, not ductile. Sorry, brittle, which means they can break easily. And ceramics have a curved shape, generally linear, and with minimal plastic deformation because it's really brittle. The yield point typically does not exhibit a distinct yield point, and fractures occur without much plasticity. The reasoning behind this is because ceramics have a strong ionic or covalent bonds leading to brittle behavior, and then the fracture occurs along cleavage planes. Similarly, glass exhibits a fracture pattern with minimal plastic deformation, and the yield point typically doesn't have a well-defined yield point because it's like a straight line mostly. And glass is like ceramics, which has strong bonds, leading to a lack of plastic deformation, and that's where like the fracture occurs without a significant strain. So we can combine all these materials together into one graph, and we can see this comparison where um, ductile polymer requires so much strain and has less like the least stress. And as you go on, you can see that less strain and more like it will cause more stress to the ceramics and glass. And you can compare it. Um, so here we can see the difference between ductile and brittle, which is like ductile metal and ductile polymers versus ceramics and glass. Ductile makes it basically at point A is where it starts to like deform, and then B is its final deformation, which it cannot go back, and then C is when it finally breaks. But for brittle, it's just a straight line, and it breaks at a point because it doesn't like deform. So overall, these descriptions provide a qualitative understanding of the stress strain behaviors for each material, and the specific characteristics may vary based on exact composition and processing of the materials. So depending on what materials we're looking at, there will be different graphs for each. Thank you.